All right, let's go ahead and get started today. Um, Greetings. It is Thursday today, at least when I'm doing the recording. And we've got some rain outside, pretty good rain. Um, and it was interesting to note that the overnight temperature was relatively warmer than it was, I'd say maybe earlier this week or perhaps this time last week when the sky was clear and the temperature would have dropped to, at least at my house, it was definitely above freezing, but it was enough to frost. So you'd wonder why the difference. It's nighttime. Why shouldn't the nighttime temperatures be the same? Uh, some good questions into which we can examine some of the reasoning that we have for why these things happen. And we can look at it from a thermodynamic situation. Let's go ahead and pick up where we left off last time. And let's take a look at, we were in the middle of doing the four processes that we were going to look at. So just going to restart there. We were looking at an isobaric process. A, I think we went into the isovolumetric or the isochoric. We did isobaric, and that was constant pressure. And we did isovolumetric, which is constant V. Awesome, thank you. We're going to do isothermal. And I think we just finished off the iso or the constant V one, and we were just about to start the isothermal one, I think. But you know, my brain is not what it used to be. Our four processes that we're going to examine in this class are going to be these four. And the first three you can see are based around the ideal gas law, ideal gas model, say. And with that, we've isolated each individual thing that is useful for a state change, uh, a difference in the characteristics of the system, right? These are all state variables. This one, though, is one in which no heat is transferred. So we would say that Q is equal to 0 for that one. Now, if we look at the PV diagrams, we've been kind of examining three different ways of diagrammatically representing these processes. We have the piston cylinder actual diagram, where we have the piston and then the gas and then it expands. I've just been doing expansion as an example. Certainly compression would work the same way. At constant pressure, we also have the bar charts, how the energy or the internal energy of the system looks before and after. And then in the middle, I have a place where heat and work can enter and leave. So we do a PV diagram also as number 3. And at constant pressure, this is a horizontal straight line. We did the isovolumetric, or I could also, the newfangled term for this is isochoric, which I'm not sure if you're going to be able to see it right there, but there it is. So we have a PV diagram that looks maybe like this. And if I did something like this, that would be number 1, isobaric. Number 2, the isovolumetric, isochoric, whatever you like. 2 would look like this. 3, the isothermal. And I think that's where we left off. If I'm not mistaken, we talked about the isovolumetric as being a situation in which no work is done because there's no area under the curve. And the work, let me write that over here. The work we found to be that. The area gives us the idea of how big the work is. And we need the negative sign because our convention is if work leaves the system, we consider the internal energy of the system to be dropping. Now, um, we have work done in the isobaric case, and it is the area of this rectangle right here underneath the blue line here. And in this case, there would be no work done here in the number 2 process of isovolumetric, such that you would be only transferring heat. Either heat would go in and the process would be going up, or it would be going, or heat would be leaving and the pressure would be reducing. So hopefully that makes intuitive sense at this point. We're going to go on to isothermal, which is number 3. And the isotherm here, perhaps what we can do is think about the first law. And think about what it would be the energy change. What is the internal energy change during an isothermal process? During an isothermal process, since the ideal gas is basically considered to be a set of independent billiard balls, right? That's kind of how I think about it. If you have a billiards table and you stack it with a bunch of billiard balls, not packed, but so that they can still move around. And then you put that table on one of those. If you've ever been to a science museum, they have one of those earthquake shakers that you stand on and then you try to make a little building and then they shake it and see if it falls over. You put the billiards table on that and then all of a sudden the billiard balls are moving around and they're banging into each other and going around. That's basically what an ideal gas is. So during an isothermal process, the temperature remains constant, right? That's what this means, constant temperature. And the temperature is really the thing that informs what the internal energy is of an ideal gas. Okay, this is one of the main reasons why we want to use an ideal gas as a system to study, to use the thermodynamics on to see what we can figure out. So during an isothermal process, the energy is constant. The internal energy change is 0 because the energy of the ideal gas, according to Joule, this is also colloquially known as Joule's law, the energy of the ideal gas depends solely upon the temperature. The internal is a function of T alone. And so if you increase the temperature, you'd increase the energy, drop the temperature, you drop the energy. But if the temperature remains constant, then the internal energy remains constant. Okay. Therefore, if that's true, then the amount of heat coming in or going out balances the amount of work getting done on or by the system. And what that means is that when I think about the energy remaining constant, what I can do is say, well, if I have a T that remains constant, and I look at the ideal gas rule, I'm asking what is the pressure as a function of the volume? Well, all I have to do is swing the volume underneath. And I see that the pressure is 1 over the volume, or it's a number over the volume. And therefore, the ideal gas isothermal process looks like this. Oops. It's proportional to, I would say, 1 over X or 1 over V or something like this, right? So I label it proportional to 1 over V so that we know that's a reciprocal curve, and not something else like half of a parabola that's been pushed over to the side or something like that. This is a 1 over X curve or a 1 over V curve. Now, in the PV diagram, you get a family of these things. Okay. So on every PV plot, you think, oh, I only have information about the pressure and the volume because it's a PV graph. But that's not 100% accurate because embedded in there are these curves, these isothermal curves. And so they go all around, right, like this. If I just draw another set here, just so that you can get an idea. Right? On every PV graph, what you don't see, or perhaps what you would have to put in yourself, in your mind, are these sets of isothermal curves. Okay? They're there, but you just have to think about them. Okay? Now, the question is, which way is temperature increasing? These are all 1 over V curves that go down like this, but which one's the higher temperature and which one's the lower temperature? So if I'm up at this one, is that higher or is this one higher or is that one lower or lower? Which one has the higher temperature? So let's see here. I thought I'd give you a look at this. Let's see. Can I do this? I'm not sure. All right. Hopefully you can see I have Desmos window open here. So I can put in here, let's say y equals 1 divided by x. Okay, so here's my 1 divided by x curve. It looks like that. Now remember, when I think about 1 over v and the pressure versus volume, if I have a higher temperature, what does that mean about what's changing? If I have P equal nRT divided by V, and I'm pushing T up, that means I'm getting a higher numerator, right? So that would mean that what I can do, oops, is go here and do, okay, what if I had a higher numerator? What if my nRT wasn't just 1, like I have in this one? What if nRT was like 5? Okay, so then I do 5 divided by x, and what would that look like? It would look like that one. Okay, what if I did y equals 13 divided by x? Well, it looks like that one. And y equals 42 divided by x, and it looks like that one. So what this is telling you, hopefully what you're seeing, is that as I go higher temperature, I'm going out that way, right? This blue line here, or anyway, this line out here is the higher temperature. This red one here is the lower temperature. So you start near the origin, which is convenient. Okay. You go, I got 0, 0, 0 as the origin, right? PV, but then T being low is near the origin and T being higher goes out. Okay. Something you probably already know. So my temperature is lower down here and it increases that way. Right? So T increases like so. Um, okay, let's ask the question, how much work is done during an isothermal process? Once again, let's take an expansion. Let's suppose that I started up here at the initial state and I'm going to end down here at the final state and I'm going that way. I just, like I said, it's arbitrary. You could certainly go the other way and find the same things. I'm just choosing final V to be greater. If I want then to find the work done by an isothermal process, I have to take I have to take my integration of the pressure as a function of volume as I have here and do it between the two limits. So this, I think you would recognize fairly easily as if I just put in the pressure here, I'll have nRT over V. The nRT we already know is constant. That can get pulled out of the front of the integration. I'm going to integrate dV over V. And as you probably already know, that would give you the log. And so your work done during an isothermal process is negative because it's work done by the gas. Remember, I'm doing an expansion. Let's see, right there. See, I'm starting here and going, no, the mirror is really weird. Okay, I'm going down. No, okay, I'm just gonna do this. See, I'm coming down the thing here, right? So as I go from a smaller volume to a larger volume, the gas is expanding. We consider that to mean energy is leaving the system and work is being done on the environment. Okay. So the negative tells us the system energy is decreasing due to this. Okay. All right. Happy days. I thought I'd show you a quick operation of an operation of a few processes here. Just to see, maybe we can take a look and see what they look like. Um, uh, oh, this is a bit leaky. Let's do this. Okay. So I have here my piston cylinder, and I forgot to bring in a little thing to open it up. So let's just pull this down a bit so you can see it, and then I will crouch down here. Okay. So what we have here is a piston cylinder, and it's connected to this tubing of this canister. And there's air. So my system would really be the air involved inside the cylinder. Okay. The system would be the air involved inside the cylinder plus the air in the tubing and the canister because that's all connected. However, that's now sealed. And in most of these problems, in fact, everything we've done so far, I've assumed that the number of moles or the amount of gas, if you like, is constant. So the N, we have not dealt with changing that as of yet. Okay. So that's a constant. This is a sealed system. And if I push this down, you see it bounces back up. Okay. Because I'm able to compress all the air. And remember, there's a whole reservoir here. So what we do here, this is the cup of warm water. So now what's going to happen is I'm going to put this in here. And maybe you saw that rise up a little bit, which is pretty cool. And now here I have my cup of cold water. Let's put that over here. So this is essentially the processes that we're talking about. Now, in these cases, I'm transferring heat in and out, and work is being done on or by, right? In this case, if I want the piston to do work, right? That's going to mean that I'm going to raise this mass right here. And so here, I'm going to put that on. You're going to watch the mass come up. I've just increased the gravitational potential energy of the mass, right? I can now actually slide the mass off. This is an isothermal process because this mass, it's a bit too small for you to see, but when I slide the mass off, and you can probably comprehend this, if I slide the mass off, the piston just comes up a small bit. right? It's no longer having to support the weight, so the piston, the gas expands slightly. That's isothermal, right? Because I've got the canister in here. This is warming all that gas. It's at the same temperature now. All this gas is at the temperature here of this water. I slide this off. That's an isothermal expansion right there. It's pretty subtle. Now I take it out of here. I put it in over here. You watch this go all the way back down. Okay. That is nearly an isobaric process. Okay, nearly. And now I'm going to put the weight back on. This will be your isothermal process. It's an isothermal compression now because I'm going to slide this weight right back on here, and I'm keeping the canister in the water. So now the gas is at the temperature of the cold water, and I slide this on, and it slightly. That's an isothermal compression. Okay. So good times. We can get usable work, right? I can get usable work by transferring heat between two reservoirs. Oops. Right there. And note, this is a cycle. This is a cyclic process. Right? I'm returning the system to near its original state of pressure and volume every time. So this is a cycle, and I'm getting usable work by transferring heat between two reservoirs as I have to, according to the second law. Okay. Up here. Okay. Now, the key is not to spill all this water everywhere. So that means we move it out of the way. All righty. Okay, quick example here. We'll throw a few numbers in and see how we do. We'll do the adiabatic as our last one. We'll move on to heat and see how we go from there. Yeah, I just want to re-emphasize this. On every PV diagram, you have the ability to recognize changes in temperature because in your mind, you're overlaying this set of curves right here. Okay. Let's suppose that we have a gas an ideal gas that we're going to expand. And we're going to do it isothermally. So it'll look like this, chugging down one of those 1/v slopes. Alrighty, what we know is that P1 is, say, 32 atmospheres. V1 is a 1 liter, and T1 is 300 Ks. What we know about state 2 is that V2 is 4 times V1. So now I'd like to find three things. That's funny. It looks almost blurry, that last line I wrote. I'm going to assume that it's blurry for you as well, and I'll try it in something darker. Alrighty, let's try again. P1, 32 atmospheres. V1, 1 liter. V2, 4 V1s. And T1, 300 Kelvin. Maybe that's better. Okay. Alrighty. Question is, I want to find out some stuff about the final state right here. V2, I kind of know what that's going to be, but what is pressure number 2? What's temperature number 2? How much heat was transferred in this process? Because remember, I mentioned this last time, if you go back to the first law, during an isothermal process, your instinct is to say no heat's transferred. No, it's just that the temperature was constant. Heat and work are balancing in an isothermal process, okay? You have to kind of separate the heat and temperature. All right, what we're going to do is we're going to try and find P2, T2, and what else? Q. Let's suppose we try and find those. All righty. Okay, V2 we already know. And so let's try and find P2. How could we find P2 here? Well, I know P1 and V1. That's helpful. If I look at the ideal gas, the equation of state for the ideal gas, I know that PV is nRT. And since I'm told that this is an isothermal process, I can right away answer the question, what's T2? It should equal T1. So T2 should be 300 Kelvin. Okay. If that's the case, which it is, I told you this was an isothermal. If that's the case, then the right side of this equation is constant and doesn't change, which means that whatever P times V I select, that's going to be also, likewise, a constant. And therefore, if I choose P1 times V1, that should equal P2 times V2. And therefore, I can solve for what P2 is by looking at the ratio of the volumes. Okay, it's just the ratio of these two volumes. Oh, well, then you got to multiply by the original pressure. So you can see if I do that, that this is 1/4 and therefore P2 turns into 8 atmospheres. Is that right? I wrote P2 twice because I messed that up. I mean P1. Okay. That better? Okay, hopefully. Oh, you can barely see it anyway, so you probably didn't catch that. Well, no problems. So P2 is 8 because the volume increased by 4, so the pressure dropped by 4. And now the question is how much heat was transferred? Well, now you have to use a little bit of first law reasoning. We know that this is an isothermal process, and therefore the Q and the W, right, are balancing each other out because the internal energy change is 0. So my first law would say that if I want to find Q, all I have to do is find the negative of W. Okay, but we know how to find W for an isothermal process. That should just be. Now I'm going to have a negative out here anyways, so that's going to take care of the negative that I had in the expression before. So I'm going to cancel those away. And it's going to be nRT multiplying, oops, I don't need that. I need the log. Sorry. Okay, here we go. I need the log of V2 to V1. Like so. Okay. And the log of V2 to V1, we know that's a log of 4. Okay, that's 4 V1s over V1, so that's the log of 4. And that's easy enough. nRT, though, we know T, we know R, we don't know N. Well, shucky darn. I guess that's the end of the example then, because we don't know N. I guess we give up. Do we give up? No, of course we don't give up. We find a better way. What's the better way? The better way is to recognize that this is part of the ideal gas rule. This is the ideal gas equation of state right here, and I can replace that with a P times V. According to this, I don't need to know the number of moles. I could just say this thing is equal to PV. So I'm going to say this is I'm just going to take P1 V1 because that's easy. P1 V1 times the log of V2 to V1. It doesn't matter which P times V I choose. I'm just going to take this one because it's got a 1 in it. I can multiply by 1 all day. Okay, so now what I'm going to do is I'm going to take 32 atmospheres for P1. I'm going to take 1 liter. I'm going to take the natural log of 4. No, I like it that way better. I'm going to take the natural log of 4. I'm going to multiply all those together. I'm going to get a certain number. What number am I going to get? Well, I don't know. But let's first off think about what units these are giving me here. The liter atmosphere? That is not tasty. I would definitely not go down this road. When confronted with something like this, a few simple unit conversions are in your future. How do you do these unit conversions? You remember that the atmospheric pressure in pascals, which is the SI unit that will make all of this work out nicely, is about 100,000. And you also remember that in a cubic meter, which is the SI unit that will make this work out nicely, in a cubic meter, there are 1,000 liters. So if I look at this, I'm going to say, well, I got 32 atmospheres. If I need to convert that into pascals, really all I got to do is multiply by 10 to the 5. Here I've got a liter. I need to convert that into cubic meters, which means I need to divide by 1,000. And I got the log of 4, which is pretty easy. The log of 4 is what? I mean, it's twice the log of 2, and the log of 2 is like 0.7. So this is a number about 1.4. I'm going to multiply 32 times 1.4, which means I'm multiplying 32 times 4, which is 128, and dividing by 10, so let's call it 13. So 32 plus 13 is about 45. And now I'm going to take the 45 that I get from this, I'm going to multiply by 10 to the 5th, and I'm going to divide by 10 to the 3rd, which means I'm basically multiplying by 100. Okay, so this number should turn out to be somewhere around, what did I say, 45? So this should be about, say, 4.5 kilojoules. Maybe 4,500 joules. I didn't write that. I wrote that a little bit close, so let me rewrite that. 4.5 kilojoules. For a little over 4,000, about 4,500. Yeah, 4,500. So that would be the heat transferred into the gas, right? Because this is a positive sign. The heat's going into the gas in order for the gas to do work at constant temperature, okay? Let's take a quick look at a piston and an energy bar chart for this, a piston diagram. The piston diagram for an isothermal, okay, it's expanding. So we start with the piston down here, and we go to here, but T is constant. So I'm just going to mark there's a T. T is constant. And that means that in order to do this, I must have supplied energy to the gas because it did work, which would have lowered the temperature, right? Because it would have lowered the internal energy. But in order not to lower the internal energy, I had to supply that much heat. So what happens here is I have a flame here, and heat's going in, and work is being done. Like that. Now, that's why I have the energy bar charts, so that we can make a little bit more sense of this. What this means is, can I do it right below? Yep, I got room here. What this means is, this is my internal energy. Okay, initially, this is the initial state. Here's the final state. That. Okay. We had equal amounts of work leaving as heat coming in. And what that means is my overall internal energy in the final state is exactly the same. Right? So there's your energy bar diagram for the isothermal process. Okay. Great. Move on to adiabatic and see what's different. I'm going to mention adiabatic now because it's a process that we're going to go through, but it's going to have some stuff in it that we haven't really talked about yet. I'm just going to let you know what it looks like, though. Uh, in the meantime, if you have a question on the isothermal process, please ask. Okay. Alrighty, so an adiabatic process, we'll just do this now, but we'll come back to this. Well, I mean, we're going to be investigating these for a while anyways. But the adiabatic process is the one in which Q is 0. In other words, I have insulated my system. All right, so my piston cylinder device looks like this. Suppose once again, I just assume an expansion. I'm going to take my piston here and I am going to clad insulation all around it. I'm going to put really good fiberglass and all of this kind of great stuff. Okay. So now what I'm going to do, I'm going to say, near, near, near. I'm going to make it into a thermos, essentially. Right? This is insulation. Such that it's not allowing heat in or out. Okay. So with that, when I expand, taste this one, like so. That I have allowed no heat in or out. Okay. So the only change in the energy of the gas will be due to its work. And in this case, since the work was done by the gas, the internal energy dropped. What does this look like on a PV diagram? Well, just before I do that, let's do a quick bar chart of this. Like so. I'm going to sketch up my isothermal lines here, just so you can get an idea, and you'll see why in a minute. Let's see. I think you can see those. They're faint. That's okay. I'm not going to use them too much. But here's an adiabatic process. An adiabatic process, an expansion, for example, might start here. And the difference is it's going to go like that. Now, can you see it's not going along one of the isotherms, right? This isotherm here goes there. Let me do this way. Okay, it goes like this and ends up over here. So this is very definitely dropping in temperature. Okay, this is an adiabatic expansion, exactly like I have diagrammed up here. And what we're noticing is that it's crossing isotherms. Anytime you're crossing isotherms, you're changing the temperature. So it's starting at one and dropping it down to another. The adiabatic curve and the isothermal curve are kind of similar. They're quite similar, but they're not the same. And it's important for you to distinguish between the two. Right now, we can't really. other than to note that, oh, that's adiabatic, and I know that it's dropping more steeply than an isothermal curve. Okay. For right now, it doesn't really matter why, how, or anything like that. I'm just letting you know that this is what it does. For this process, it's not a PV equals constant. It's PV to the gamma. It's PV to an exponent equals constant. And therefore, this makes it drop slightly more steeply. It drops more steeply than an isotherm. Okay. I'm not going to explore any more of that right now. We will come back to this, but right now we don't have quite enough to be getting along with this because we don't know what the exponent is. We'll figure out what the exponent is a little later. But those are the four ideal gas processes that we're going to explore in this class. And I want to make sure that you become familiar with the three graphical representations for each. In other words, the piston cylinder drawing, the bar chart for the piston cylinder, and the PV plot or PV diagram showing the actual process on a PV plot. All righty. So those are the three ways to represent the processes. We have four processes, so just please become familiar with how to do that. All right. So that is pretty much work. Other than, at least for the three main processes that we can handle right now, I'm also not going to really discuss the work done by an adiabatic, but you can see that there's area underneath this. Okay, so we can find that in principle. I just don't want to do any of the mathematics right now. It's not useful because we don't have a background for it. Okay, so let's do this. We started all of this back on I guess yesterday. I guess it was only yesterday. We started all this because we looked at the first law and we said, okay, the first law, I'm just going to erase this here. Okay, the first law is this, which we know. And I said, well, we are going to undertake looking at each quantity in turn. We've examined the work done. In doing that, we have already kind of looked at what the internal energy specifically for the ideal gas is going to be. Okay. So now let's move into heat and talk about what properties of heat we can come up with here. All righty. So so let's look at heat. Essentially, we're going to talk about the amount of heat transferred and what are its consequences. All right. We can start with thinking about a connection which is probably very familiar to you, which is that if you supply heat to something or you remove heat from something, then its temperature changes. Right? So let's look first at heat and temperature change. Now, I have tried to be kind of clear to say, remember, this doesn't always imply one another, right? Just because I have a temperature change does not necessarily mean heat was involved, right? Because of this, right? I've got heat, I've got work, and this thing over here is basically where you see the temperature change. So what we're doing now is we're saying, okay, suppose that for a minute we don't think about work. Let's focus only on heat. what's the effective heat if there's nothing else happening. All right. So this is the mode that we're taking right now. What we're going to do is we're going to think about what's a sensible outcome for this. The sensible outcome is when I supply heat to something, its temperature rises. Or if I take heat away, its temperature drops. That's sensible, right? So there's something called, and I really like this term, it's called the sensible heat. Um, you know it by a different name these days. Um, hold on a sec. I just have to refill my black ink here. You know it by a different name, and the different name is the uh, well, you cut to the chase. It's the specific heat. Okay. But first, before we hit specific heat, let's talk about heat capacity. The heat capacity is essentially how much heat is necessary to increase the temperature of a sample by a degree, or how much would be needed to be taken away to drop the temperature of the sample or the system by a degree. Right? So we talk about the heat capacity as I'm going to use bars on my C here to show you that it's capital. All right, so it's essentially how much heat is transferred for a given temperature change. Now, that depends on how much material you have. Okay. If I try to change the temperature of a glass of water, I can do that relatively easily. If I try to change the temperature of the ocean, not so easy. So the ocean's heat capacity is huge compared to even if I just went to the ocean and I dipped a cup of water out, I can change the temperature of this much more easily. Its heat capacity is much less than the ocean's heat capacity. So you think, well, wait a sec, it's the same water. This is seawater, that is seawater. So shouldn't they have the same tendency to absorb and reject heat? And the answer is yes. What you're going to do is you're going to say, well, I can do this by mass. Okay. I can do this by the mass of the thing. And this is what's called the specific heat capacity. Right. So this is the degree. This is the same type of thing. How much heat does it take to increase the temperature by a degree, say? And usually it would be a degree centigrade. But you would factor out how much mass there was. When you do that, then you're going to say, the specific heat capacity is really an indicator of what material it is. It's a material specific property. This is denoted with small c, and it goes by m times delta T in the bottom. So this is the amount of heat, Q, necessary to change a particular amount of material, mass of material, by a certain temperature. All right. So this will be Q, which is the heat transferred. Mass, we'll go ahead and stick with kilograms for the mass temperature change. The temperature change, now since this is a temperature change, we can use centigrade. You are certainly welcome to use kelvins for this. Delta T in Kelvin is exactly the same as delta T in centigrade because they're just offset by a constant value, right? So no matter what you are on the Kelvin scale, 100 is the same as 100 on the centigrade scale. Now, it's not the same on the Fahrenheit. We'll talk a little bit more about this a little bit later. when we talk about temperatures, but Kelvin and centigrade make no difference. When it's a change, okay? If it's just straight up T, you can't use centigrade. If it's a delta T, you can use centigrade. Okay, so let's take a look at what happens. Uh, let's take a look at what happens if two objects exchange heat with one another and come to a final equilibrium. This is the science called calorimetry. We might as well do this in the backdrop of an example. So, suppose I take a chunk of hot aluminum and I drop it into water. Okay. And I'm going to say, well, I'm going to insulate the container of water. It's a bucket, say, or something like this, but I've got insulation around it. So there's no heat in or out. And that means that the aluminum and the water are exchanging heat, but they're not letting the heat come out to the environment. Okay. Now, I'm going to suppose that we know some stuff like, well, water. We know things like the initial temperature of the water and the specific heat of water. And we're going to know things like the initial temperature of the aluminum. My question is, if I measure the temperatures, can I find what would be the specific heat capacity of aluminum? Right? In other words, remember, this is essentially a material dependent. This is different for different materials. So my question is, what would it be for aluminum? Okay. Let's take a look. This is a process known as quenching. And so I'm going to assume that we know things like, here's our picture here. I have this insulated. This is a block of aluminum. This is water. So what we know are things like the masses of the aluminum and the mass of the water. We know the initial temperature of the aluminum initial, and the initial temperature of the water. We know the final temperature, and we know the specific heat of water, with the specific heat capacity of water, okay, which I call CW. Now, historical note about the specific heat of water. As with many things, water is the standard. So when people said, we need to define an energy unit, what they said was, okay, let's just take a cup of water and see how much, whatever amount of heat it takes to raise the temperature of the water this much, we'll just call that 1 calorie. So the specific heat of water was 1 calorie per gram. And per 1 degree, in order to raise the temperature by 1 degree. Or a 1 degree change. 1 degree centigrade change. Okay. So let's suppose then that if you remember a little ways ago, you suppose that you remember the mechanical equivalent of heat. So since this was given in calories, and we know how many joules there are in a calorie, then we basically know what the specific heat of water is because it's 1 calorie per gram. And therefore, if I know how many joules are in a calorie, then I know how many joules there are that's going to need to raise the temperature of water by a degree. So commonly, this is something like 4190 or 4186 or something like that. Any of those numbers will work fine. I'm probably just going to round it off to 4200. And we'll use, for this, we'll use joules per kilogram centigrade. And it's large because I've changed the grams into kilograms. And the 4 comes because there are 4.1 or 4.2 joules per gram, joules per calorie. Yeah, got that right. I think I did. Anyway, let's set this problem up. They exchange heat only with one another. Since the aluminum is giving off heat and the water is absorbing it, we could imagine that the Q from the aluminum is negative, the Q from the water is positive. And so in order to make the Q from the water positive, I just got to have a negative in here. All right, so that's going to, and since the Q of aluminum itself is going to be negative, there's a negative involved there. The other option for this is to just forget all the negative signs and put absolute value bars. That'll work too. All right, since I can find how much heat's transferred if I just take the denominator here and swing it up, I'll be able to say that the aluminum had a temperature change of delta T aluminum, mass of aluminum, and all this is aluminum, aluminum, and the heat of the water is water, water, and delta T water. These two should equal each other. Minus aluminum, C aluminum, delta T aluminum. Like so. And what I'm looking for basically is C of aluminum. So all I'm going to do is just take all the rest of this stuff and chuck it to the other side. Now, you might be a little bit nervous about this negative sign, but realize that I've got a delta T in here. Why do I want to make sure that I've got a negative sign in here? This delta T is going to be negative. Its final temperature, the aluminum's final temperature is lower than its initial temperature. So this delta T is going to be negative. I want to make sure that that negative gets taken away by this one so I end up with an overall positive quantity. Okay, so just by dividing the stuff I had over here on the left side and chucking it underneath the right side, I'll have an expression for the C of aluminum. I'm going to take a quick moment right here to say that I worked out the algebra in this case because it's relatively straightforward. Now, suppose that I knew what the heat capacity of aluminum was, but I was looking for the final temperature. That's going to involve much more algebra. I typically, to come to a final expression, it's going to require a lot more algebra. I typically say complete all your algebra before putting numbers in, and this is going to be one of the exceptions to that. What you're going to want to do is get to a point where you have a reasonably straightforward expression and then just start simplifying by, if you need to put numbers in at that point, I put numbers in. The algebra just becomes so messy. And it doesn't lend very much to the problem because we already kind of have the physics sorted out. So bear that in mind as you attack the calorimetry problems. Okay. Now, if I knew things about this, if I had measured these numbers, I could put in numbers for this. And it turns out that I went ahead and picked a few numbers to do this. So let's do that. I have a kilogram of aluminum and 10 liters of water. Okay, so what I had was a kilogram of aluminum and I had 10 liters of water. Oh, but that's not the mass of water. Remember, water is great because it's one of these things that was used as the standard, right? It's the thing that freezing and boiling, we measure our temperatures with respect to, right? Well, when we think about the mass of water and the volume of water, it's the same thing. A liter of water is a kilogram. So this is 10 kilograms worth of water. Right? Because I know that in a cubic meter, there's 1,000 kilograms, but in a cubic meter, there's 1,000 liters. So there's 1,000 kilograms and 1,000 liters. It's one. That's the great thing about things like the heat capacities and the densities. Everything's one when it comes to water. If you just pick the right units, which nobody does these days. Suppose that I have a temperature, a final temperature of 21.3 centigrades. The water was initially at 20 centigrade, but the aluminum was initially at 80 centigrade. If I plug all of these numbers in, I can do that here. Let's do this. The mass of water being 10 kilograms and the mass of aluminum being 1 kilogram. Okay, so mass divided by mass. The specific heat of water, 4,200 joules per kilogram centigrade. So that's the units that I'll come out with in my aluminum specific heat capacity. And then the delta T for water, final minus initial, you can see is going to be 1.3. And the delta T of aluminum, I'm going to factor this minus through into the delta T of aluminum. Now, this would be final minus initial, right? So normally this would be 21.3 minus 80, but I'm going to pull the minus through. So 80 minus 21.3, that would be 60 plus 1.3. So I guess it's 58.7. That seems to be okay. Is that about right? Anyways, just quick inspection of these numbers reveals compared to the specific heat of water, I'm going to have something that by mass is going to be 10 times greater, but by temperature change is going to be 50, almost 60 times smaller. So I would expect the specific heat of aluminum to be about 6 times less than water from this. And that's typical, right? When you go sit on an aluminum bench, right, you feel cold, but then it's kind of gone pretty quickly, right? And then you can kind of get up and feel how warm is this? Actually, the amount of heat you transfer to it causes temperature to rise pretty quickly. Well, or it rose a lot comparatively. Let's see, if you do this, I got, what I got? I got 930 joules per kilogram. If you did joules per gram, this would be 4.2 and this would be 0.93. Is about what I got there. Okay. So that is what happens when heat is added and we expect a temperature rise, or I should say a temperature change. If heat is transferred and we expect a temperature change. This is kind of how our brains are wired because every time heat comes in, you go, oh, that's getting hotter, right? Oh, heat's coming in, that's getting hotter. Oh, heat's leaving, that's getting colder. What about the situation in which heat's transferred and there is no temperature change? Heat transferred with no delta T. Well, it does happen. And instead of causing the temperature to change, the heat's effect is to cause something else to change. Okay. What it can cause is a change of the state or the change of the phase. Okay. Change of phase meaning gas, liquid, solid. These transitions occur when heat is transferred between them, between the system and the environment, into or out of the system. Um, but no temperature change is happening because they are at what are called the phase change temperatures. The changes happen at particular temperatures. Now, please note that when I'm thinking about this, I'm thinking of the bulk of the material. Okay. Now, phase changes can happen at the surfaces of materials very easily and not at the phase change temperature. Okay. This is known as, if you take liquid, this is an evaporation. Okay. That can happen at any temperature. That's a phase change. I'm talking about the entire bulk of the system, right? The entire thing has been moved up, up, up in temperature. And finally, it's all here. And now it's becoming this other phase. Okay. So pot of boiling water, right? You put it on the stove, you heat it to get the water towards boiling, and then eventually the whole thing is now boiling. When that's all happening, are you losing water from the top? Absolutely you are. And it's not at the phase change temperature. That's not what we'll talk more about that later, but that's not what I'm getting at here. So um uh, phase, these changes of phase occur at constant temperature. And therefore, the heat is not having the effect that we expected, and therefore we call it hidden. It's hidden heat. And another word for hidden is latent. Latent meaning hidden. Right? Because we're adding heat and we're not seeing a temperature increase. So it's like the heat's going into the material and then it's hiding. I kind of like that. Sensible heat, which is what you expect, and latent heat, which is hiding from you. So if you are to, for example, plot the temperature of a sample of, say, ice, you take ice out of the freezer and you warm it up, it would look something like this. Temperature versus time, and I'm going to go ahead and say this is the temperature in centigrades, starts out of the freezer. So we're looking at something that's maybe minus 15, minus 10 centigrade as it comes out of the freezer. Zero is here, so it's going like this. There's minus 15 centigrade. This is ice. Okay. It stays here for a ways because it's now changing from ice solid water into liquid water. The temperature is 0 centigrade at that point. When it's now a liquid, we keep heating it up. And we get to here, which is 100 centigrade. I know my scale is not very good, but that's the way it goes. At which point it flattens out again, and now it's boiling, becoming steam. Like so. Now, a couple of things you might notice. Number one, the slopes are all different. This slope is pretty high, that slope is pretty high, this slope is fairly low. Another thing you might notice, this plateau is much longer than this plateau. Okay, these are not accidents. Since we're talking about latent heat, we can talk about the plateaus. The plateau here indicates that it's much harder to boil water from liquid to steam, liquid to gas, than it is to melt it from solid to liquid. That is true. And why that is, perhaps we can investigate later. But the idea is a bonding phenomenon. Okay. So, and this is essentially true in general. What's called the latent heat of melting, or if you go backwards, latent heat of fusion, is less than the latent heat of boiling or latent heat of vaporization, or if you like, the latent heat of condensation, whichever. I mean, these are all reversible processes, so you can use the same thing for both. The slopes indicate the specific heats, okay? So the specific heat of the liquid phase is very low. Sorry, the slope of the liquid phase is very low because the specific heat is very high. I got it wrong backwards there, but I got it corrected up. The specific heat here is big, which means that you put in this huge amount of heat and you get this tiny little temperature increase. And then you put in this huge amount of heat and you get another tiny little temperature increase. But it takes a lot of time to increase the temperature of the liquid, whereas it takes much less time to do the liquid, the solid or the gas. Okay. Okay. So when you're talking about latent heats, since there's no temperature change, it's simply a number that quantifies how difficult it is to change the phase. The latent heats here are given by a Q, which is the mass of the sample multiplied by L, latent heat, and L is just a number which characterizes how difficult it is to go from one to the other. It's a phase change number. No delta T involved here. Okay. As I'm looking at the clock, I'm realizing we have a few minutes left, so I will start by setting up the example that I wanted to do involving latent heats. But that means we are going to have to put it aside until next Tuesday. And I wanted to also do another example involving some proofs. Like I asked one specific question on the homework. So let me set up the example here, and we won't finish it, but we can at least pick up straight from here on Tuesday of next week. So here's the example. I want to drop some ice cubes into liquid water, or things that can be modeled as essentially pure liquid water. What I'm going to do is I'm going to say, okay, suppose that I know the mass of the liquid and the mass of the ice cubes, okay? And we're going to look at the initial state as being 2 ice cubes, and they're fresh out of the freezer, okay? So we suppose we know their temperatures. Did I say minus 15 for these? Yep, I did. So initial temperature of the ice cube minus 15 centigrade. I'm going to drop these 2 ice cubes into liquid. And I'm going to suppose that I have 200 grams of the liquid water. And that's what? That's a 2/10 of a liter, a fifth of a liter. So basically almost, it's going to be what? 8 ounces worth. Yeah. And what I want to know, and this water is at an initial temperature, all right? The water's initial temperature, let's say, is 25 centigrade. T initial here is 25 centigrade. And the question, which is not really a question, is describe the final state. And that means we have to investigate some stuff. So, do the ice cubes melt? If so, do they fully melt? Does the water fully freeze? What's going to happen? All right. So we'll pick up with this on Tuesday of next week. I will say here in the last couple of minutes a few housekeeping notes. Number one, lab kits are available. We're going to have a lab. I'm going to post the lab and have a little video on lab. I will just be posting it tomorrow, so you should be able to go ahead and get started. To pick up a lab kit, you have to come to the Aptos campus, room 800, room 802 in the 800 building, and talk to Julia. She will sign out your lab kit to you if you have not gotten one already. And that is due back to us by the end of the semester. So please try to make sure you don't lose any of the pieces. Um, should you not be able to do that, please send an email to her or me, and I'll forward it to her with a mailing label, a shipping label. Okay. And so we are happy to ship these to you and then please ship them back at the end of the semester. PLC is due tomorrow. The PLC is a quiz style PLC, so you should be able to just check answers. You do get 3 attempts at it, and after that, it's going to cut you off. So try to make sure that you're all set with that. Um, and homework, I would recommend getting started on the homework, looking at some of the concept questions. And given today's stuff, we can look at more of the calorimetry problems that occur. And with what we get done on Tuesday, we should be all set to go for homework being due on Wednesday. And with that, I say happy rainy day. At least it's raining here. And so happy rainy day. Happy rainy day to the rest of you. And I will see you well, I don't know if I'll see you tomorrow in the lab stuff, but a lab stuff will be posted tomorrow. Um, and after that, that's it. So happy weekend, and I'll see you again on Tuesday.
Oh,
Marcus.